Okay, so last time we talked about the idea of least squares as a projection operation in a linear model. So we had the y is equal to x beta plus some noise and or some error. And then we try to minimize the sum of squares of errors, which gives you this least squares problem over beta. And then this is equivalent to minimizing mu in the image of x, norm of y minus mu squared. So this one would be a projection operation. Okay, so they're equivalent. So if we're sticking a vector mu in the space image of x, such that its distance to the observation vector y is minimized. And so we had this geometric picture. Mu is the true mean, or let's say the true signal part. So far, we don't have any random assumption on y, so it's the structured part of y, and it lives in the image of x. And then there's this noise, which we add to get the observation. And so because of this noise vector or the error vector, y is outside that subspace. So the best that we can do is kind of project onto the subspace. And because of the error, we're not going to get exactly the mu, but we're going to get this mu hat, which is the projection of y onto the image. And what we know is that this error of projection or residual, if you want, is orthogonal to the image. Okay. So we have this E, which is y minus mu hat, which can be written as x beta hat, is orthogonal to the image of x, which implies that sort of equation. So x transpose E is equal to 0, so if E is in the kernel of x transpose, which then implies that beta hat satisfies the normal equation. So you end up with this familiar formula under the assumption that x has full rank, full column rank. Okay. And there are a lot of things from this picture that you can observe. In particular, what we can observe, I mean, both mathematically or like algebraically and also later on, maybe geometrically. So if I look at the x beta hat, that will be mu hat. If I plug in beta hat, I get x times x transpose x inverse x transpose y. Okay, and so there's this matrix here, x times x transpose x inverse times x transpose, which when multiplied by y gives me the projection. So this matrix has a kind of name, regression usually. What does it, or has anyone seen or know the name? Yeah.
Orthogonal projection matrix.
It's an orthogonal projection matrix. In regression, they call it the hat matrix, but orthogonal projection is a better linear algebraic name. So you might denote it as H. It's an n by n matrix. So X is n by p plus 1. The middle guy is p plus 1 by p plus 1. And the X transpose is p plus 1 by n. So really, once you multiply out, it's n by n. So if you remember a matrix, you view it as an operator. So it maps vectors in Rn to vectors in Rn. So this particular one has this geometric interpretation. It takes a vector y and maps it to the projection of y onto the image. Okay, it has a very nice action. And so for that reason, You can call it the projection matrix or orthogonal projection matrix. Right? How many people have seen this matrix before? Nothing. Okay, one person. Okay, two. So this matrix has properties. In particular, it's a symmetric matrix. If you just try to transpose the expression, you get the same thing because the middle matrix is symmetric. And it's idempotent. Okay. What does idempotent mean? So H has the property that H is equal to H transpose and is idempotent, which means that if I square it, it's equal to itself. Okay, so this particular one is, and so these are actually defining properties of the orthogonal projection matrix. So the matrix that has these properties is an orthogonal projection matrix. The second property, idempotence, is so you can just multiply things out. So H squared is just H times H. So this really means H multiplied by H. So you multiply it out, the expression for H in terms of X is there. And so you'd get that is equal to H, but geometrically it has a very interesting interpretation. Anyone can see what it means geometrically? So if I do, for example, H times HY, so this expression is equivalent to saying for any vector, so let's say a star is equivalent to saying for any vector y in Rn, H applied to Hy is equal to Hy. Then this gives me, yeah. Yeah, so this means H is idempotent, but I'm asking what is the geometric meaning? Yes.
You're projecting onto the same subspace twice, so the second projection is.
Yes. So exactly. So this is saying if I project a vector once into the subspace, something might happen. Okay, so I projected once. Okay, this is something going on, but once I have it, this is going to be Hy. This lives in the image of X. And so if I project it again, for any vector that's in the subspace, projection is not going to do anything. So it gives you back the original vector. So projecting another time, so applying H to this is projecting Hy again. So that doesn't change the vector. Okay, so that's the property of projection. So projection once is doing something, twice it's just not changing anything. Yes.
For this, is this only for idempotent matrices, or is it for any matrix transformation?
So this particular matrix has the property that it's a projection matrix.
Yeah.
And projection matrices have this property. They're idempotent. Not for any general transformation.
So only for idempotent.
True. So idempotence is equivalent to this, but so the statement is this. If you have a projection matrix, it's going to be idempotent. Why? Because of this geometric fact. So if you have an orthogonal projection matrix, it's going to also be symmetric. So these together define an orthogonal projection matrix. You could project in an oblique direction. It still would be idempotent, but it's not going to be symmetric. Okay, so idempotence means something about projection. So any idempotent matrix is projection onto something, because if you do it twice, you're not going to get anything. But together, they define orthogonal projection. Does that make sense? It's not obvious. So what we showed is like we have a projection matrix, it's idempotent, and it makes sense. The other claim that I'm making is stronger. So any idempotent matrix is projection, not necessarily orthogonal onto some subspace, which we don't worry about. Yes.
And in the idempotent operation, does the y change? Like, does the vector change? Is it that a transformation can happen, but it stays in the same subspace? Or is it that?
No, the first time you do, something happens. So the first time you have y, you apply it, potentially change the vector, you get this. But if you apply it again to this vector, nothing happens. Like nothing means like the vector is the same. That's yeah.
I know how the H, for example, projects onto the, I guess, H space. What about
Projects onto the image of
Yeah,
X,
image of X.
which happens to be also equal to the image of H. Okay, now go ahead.
Yes, what if you, is there idempotent properties for like, I guess, inverses? Could H inverse be idempotent?
H inverse could it be idempotent?
Like, idempotent in the sense it goes from the image of X to the non-image of X.
So do you think H is invertible or not? Let's ask this question. Is it invertible? Is an invertible transformation?
I don't think it's gonna be that like at least one in this case, because
Fair enough, one.
because I'm assuming R is spanning like 3 because the fact you have E. Because E is implying that there's some like orthogonal basis stuff there. In that case, that means the kernel is at least greater than 0, which
Dimension of the kernel.
the dimension.
So you're on the right track, but like, can you explain it a little bit simpler? It's true, it's not invertible. Why it's not invertible? What does it mean to be invertible? What does it mean for a transformation to be invertible? Can you explain it easier? The answer is correct. It's not invertible. But why it's not invertible? Yes.
That's you can explain it as in transformations that if you can undo the transformation, it's invertible, so you rotate it this way and rotate it back. It's invertible.
Yes.
But if you project, you're losing information, so you can't project it.
Okay, good. You lose information. There are multiple things. Let's say everything here is going to project, all these vectors are going to project to the same thing. So once I know the projection, I can't identify which one was it. So anything in this direction will project. So you lose information. You lose the direction. Let's say that's orthogonal if you want, if that was the. So any information in this direction is going to be lost. Any information in the orthogonal direction would be lost.
Should probably communicate that instead of saying the kernel
Yes.
is greater than 0.
Yes, that would be better. So you say the information in the orthogonal direction is lost, so you can't recover back. So you can't say what is the height, let's say, relative to this thing. Yes, if that was your intention, that's the correct way. Yeah.
I just say information.
Yeah, information loss is like the key. Okay. Information is lost, transformation is not invertible. Okay. Invertible transformations don't lose information. Let's say rotation, you can rotate it back. But so H is not invertible, so the question, like, you can't say like, is the inverse idempotent or not? So there's no inverse. Sounds good? Okay. So you can see geometry tells you a lot about, once you know that this is projection matrix, you can reason a lot about properties. H is not invertible. There is information loss in the orthogonal directions, or in the direction of the orthogonal complements. Any more questions? Let me summarize it here so we already see this. So this is called the hat matrix, perhaps, because it puts the hat on Y. I mean, this is sometimes called written as Y hat. You're not going to do it. Use mu hat. So H is an orthogonal projection matrix onto the image of X, which happens to be also the image of H. This you can also reason for yourself that the image of X and the image of H are the same. So it's like once you project everything in Rn, you cover kind of the entire image of X, which would be the entire image of H. So as Y varies in Rn, HY covers the image of X, which also happens to be like covering the image of H, so they're the same thing. And so you start from some X with certain columns and you form this H. This H is going to be associated with the subspace. So you lose the information about X. So there could be multiple different design matrices that once you do calculate this projection matrix for, you get the same projection matrix, okay? Projection matrix kind of uniquely identifies as identified by the subspace. Not necessarily, you don't need to worry about the X and underlying it anymore. I could have chosen different bases in this subspace I mean, this basis or this other basis, this will give me a different matrix X that will produce the same projection matrix. So once you lose that information, it's just everything is encoded in the edge itself. Okay, so this is one of the homework problems that you see, like you change the basis by multiplying X on the other, like on one side by a like a invertible transformation, it would give you the same edge matrix. Okay. What else? Okay, so another interesting point is I minus H is also going to be a projection matrix. And the easiest way to see, first we note that really the error can be written as y minus mu hat, which is 1 y minus hy, also I minus h times y. So this I minus h is really kind of applied to y is giving me the error or the residual. And it happens to also be a projection matrix. It's in fact projecting onto the orthogonal complement of the image. So the easiest way to see is recalling this decomposition. So you can write y as hy plus I minus hy. And the fact that I can do it is just simple algebra, right? So this just evaluates to y minus hy, and you can see hy's cancel out and you get y. So every y can be decomposed like this. We know that this is the projection of y onto the image of x, or image of h if you want. We call this mu hat. This would be the error or the residual, and it belongs to the image of x perp. And you see this orthogonal decomposition. We decompose the vector into a piece which is in the image and a piece which is in the orthogonal complement. But the composition kind of symmetric. Whether you treat this as the projection and this is the error projection is in like the eye of the beholder. So you can look at this as the projection onto the image of x perp and this as the error projection. Why? Because I can think of this as a V, as a subspace, right? Then I note that mu hat is in V perp. So because maybe remember the image of x perp gives me back the image of x. We know that mu hat is an image of x, so it's really in the V perp. So we have y decomposed into a component in V and a component in V perp, so that E has to be a projection because the difference is orthogonal to V. Okay, so this is really a dual decomposition. There's no like, let's say, advantage of one to the other. So one, if you think of one as a projection, the other is the residual, or the other one is the projection, the other is the residual. For us, usually we think of this part as the projection. So H is going to be the projection onto the space that we want. I minus H would be the projection onto the space that we kind of don't want. And you can actually easily verify that really algebraically this satisfies the property. So I minus H is both symmetric and idempotent. Just multiplied out, squared, and it follows that it's idempotent and also symmetric. So it's really a orthogonal projection. Yes.
The image of I minus H is, I guess, for Y is like perpendicular to the.
Sorry, let's go to, you're looking at the image of I minus H.
No. I mean, like projection of I minus H is perpendicular to the image. Does that mean it's the kernel?
Can you say that again? So projection.
So since you can see that E is like the space of the image of X transpose. And that's like I mean orthogonal. Since it's orthogonal to U hat.
So sorry, what are we looking at here? So
U hat is image of X. E is
there's no U. There's no U. Oh, mu hat.
U
Okay.
hat.
Mu hat. Okay. So mu hat is an image of X. Okay.
Yeah, and then the E is orthogonal to it. Does that mean that E is the kernel or the null space?
No, it just means that E is in the kernel of X transpose. This we already saw. Okay, so E is in the image of X perp, which happens to be the same as the kernel of X transpose, so it just means that E belongs to the kernel of X transpose. Yes, so we actually use that, yes. But I thought you were talking about the image of this, which is good. So what is the image of I? Let me ask this question. What is the image of I minus H?
I minus.
It's a matrix, it has an image.
Probably due to the property of how it could be split up, I assume it's the image of I.
It's going to be image of X herp. Okay, it's projecting onto that subspace. It's going to have, the image is going to be that subspace, whatever it's projecting onto would be. Okay. Image of H, like image of H is image of X. That is that. And then image of I minus H is image of X perp. So once you see the geometric picture, then all of these questions should be easy to answer. If you don't see it, you can like struggle a little bit with the formula, which would give you the same answer. So you try to prove what is the image. You have to look at like I minus H times beta or something else, and then vary beta and then argue. But if you see it, then you don't have to worry. Sounds good so far? So this is the H, I minus H, and the projection operation. This matrix is very useful. Actually, I did it in the morning class, so let me quickly say, so what we can do is that because H is symmetric, implies that it has an eigenvalue decomposition, okay, EVD. Because, so remember, the eigenvalue decomposition is, you have U lambda U transpose, U is a matrix that has eigenvectors as its columns, and lambda has diagonal entry being eigenvalues. And so if I square it, so this always is true for a symmetric matrix, of which H is an instance. So H squared, what would it be if I square this? Yes.
We know H is idempotent, so we just use the same equation as.
Okay, so that was clever, but I want to use I want to square it and then set it equal to H. So let's say I don't know, yeah.
Lambda squared.
Yes, U lambda squared U transpose. So if you haven't seen it, I encourage you to try just multiply. I mean, you have to do this, U times U lambda U transpose. And then this would be identity, you would get U lambda squared U transpose. Do it for yourself as an exercise. So this holds for anytime you do the spectral decomposition or eigenvalue decomposition, you would get this. But now we know that it's equal to H, so I'm going to set it equal to U lambda U transpose. Then you can multiply on both sides by U. I'm going to multiply both sides by U transpose on this side and U on the other side. So this equation in between, multiply both sides and then use the properties of U. You conclude, and this is an exercise for you, you conclude lambda squared is equal to lambda. So U is going to go away. And these are diagonal matrices. So this just means that lambda I squared is equal to lambda I for all I. So imagine two diagonal matrices are equal. I mean, coordinate-wise, diagonals have to be equal. So this is a little bit fast, but I want you to do it as an exercise. Yes?
Symbol is for this H.
So this operation, if you write H like this, then this is always true, if that's the spectral decomposition. Then the second equality, this one, is by idempotence.
Yeah, so it has to be symmetric and idempotent. So
For this to follow, yes. And this has a special, like lambdas are the eigen, like the diagonal matrix of eigenvalues. So we proved that lambda I squared is equal to lambda I for all I. What does this tell you about the eigenvalues? What is the solution of this equation? It's like a quadratic, yes.
The eigenvalues can only do 1 or 0.
Yes, so this is like x squared minus x is equal to 0. And if you solve it, the solution is either 0 or 1. So this implies that lambda I is either 0 or 1. So So like a projection matrix, we're talking about projection matrix has eigenvalues that are either 0 or 1. Okay, this is another interesting fact that comes out of these properties. And we can actually say how many of the eigenvalues. So there are n eigenvalues, and then repeat it. So how many are ones? How many are zeros? Anyone has a guess? So X is a matrix which is n by p plus 1. And let's say it's full rank, full column rank, which means that the dimension of the image of X is p plus 1. And this guy is projecting onto that subspace and has the same image. So, yes.
P plus 1 eigen. No, eigenvalues.
Yes, p plus 1
Eigenvalues.
of eigenvalues would be
Not eigenvalues. You should.
would be ones. Yeah, eigenvalues are scalar, so exactly p plus 1 because the dimension of the image of X, which happens to be dimension of H, which means that it's the rank of H. So rank of H is p plus 1. And the rank of a matrix is equal to the number of non-zero eigenvalues. Okay, and so because the matrix is n by p plus 1, so this is going to be the number of zeros, number of zero eigenvalues is n minus p plus 1. Okay, so n minus p plus 1 would be 0, and then p plus 1 would be 1. So we know kind of everything. And if we can go a step further, I can partition U into columns like p plus 1 columns here. Let's call the rest Q. N minus p plus 1 is Q, let's say. So p plus 1 columns and then Q columns here. And then the lambda in between would be I, p plus 1 here, 0, 0, 0. Then you get U transpose here, U2 transpose here. And then you multiply out, this is like a block partitioning of U according to which eigenvalues are identity or 1, which ones are 0. You do the block decomposition, and then you multiply out, you get that this is equal to actually, so this is H equal to U1, V1 transpose. Okay. So this simplified form is like simplified, like a truncated eigendecomposition. So you just keep the eigenvectors associated with eigenvalue 1. That would be a matrix which is going to be n by p plus 1, and then times U1 transpose. So something like this you do in your homework. You can do the same for I minus H, because that's a projection matrix, but for I minus H, the zeros and ones are flipped, because the dimensions are flipped. Okay. So you go through this, you learn a lot. Yes?
Why is the zeros do we not show like n, I guess n minus 1?
So once you multiply out, I mean, this would give me like U1 times the identity times this plus the rest of the things would get multiplied by the zeros and then it would vanish. So you get 4 times 2 of which are 0. 1 is only there. Okay, no, remove this to avoid confusion. So this is a little bit fast, but I just want you to go over it yourself to realize all of it. So starting from the idempotency and symmetry. Symmetry gives you the eigenvalue composition. Idempotency gives you this equation about the eigenvalues, which you conclude from which you conclude that the eigenvalues are either 0 or 1. The number of ones has to be then the rank of the matrix, which happens to be the same as the dimension of the subspace onto which it projects, which happens to be p plus 1. And then, so you rewrite the decomposition by splitting the columns of U according to the eigenvalue being 0 or 1. And then you multiply out, you get this simplified form. Okay, which is very useful. So U1 still has this property that U1 transpose U1 is identity, but the other way around is not true. So U1 transpose is not, because it's not a full orthogonal matrix, but this still holds because the columns are orthonormal. Anyway, so this there's a lot of things that you can do, but just like a footnote, which will be useful for us later. Okay, these projection matrices kind of don't scale things. If you remember what eigenvalues are, they keep some of the directions exactly as is, they collapse the rest of the directions, okay? They don't scale by 2, for example. Anything like these eigenvectors are preserved exactly. The projection just doesn't distort, it just like removes some of the dimensions, okay? So it just removes the directions along these 0 eigenvalues and then keeps the direction along the 1 eigenvalue exactly restored. That's another geometric meaning. Okay, I think a lot of linear algebra in this slide. Any questions? Comments? Okay, so let's move on. I mean, let's do some statistics. These properties are going to be very useful for us throughout the course. So far, everything has been deterministic, like geometric and linear algebraic or deterministic geometry if you want. And so given a vector y and a capital X, these are like numeric constants. Let's say I just, even in R, you get a vector of numbers and you get a matrix of numbers. There exists an image of X. I can project onto it, so I get mu hat and E. These are all like numeric objects, let's say, or abstract linear algebra like concepts, but they're perfectly well defined. There's no statistics here, okay? You give me a Y, I give you mu hat and E. As an X, I give you mu hat and E. To do statistics, we need like a statistical model to be able to quantify, for example, how good this beta hat is as an estimate. Okay, and for example, how uncertain we are about the coefficients to build confidence intervals and so on. So we need a statistical model. So I'm gonna maybe spend a few minutes just making sure that you understand what this means. So we're assuming now that y is actually equal to x beta for some true beta plus epsilon, which is a random vector. Okay, so this is going to be a data generating process. And the key is that I'm going to assume that this is a random vector. Before it was just some like, getting our hand around what this is. Now I'm going to assume it's a random quantity. And because this is a random quantity, y would be a random quantity. And because beta hat depends on y, beta hat would be a random quantity. So now what I mean by randomness is that we're living in the abstract world of probability. So the key here is that this y is not going to be just what is called a vector of numbers anymore. Okay, it could be many different vectors of numbers. Okay, so it's if I do the experiment once, I get a vector of numbers. If I do it twice, I get another vector. If I do it many times, I get many different. So I get infinitely many y's because there are infinitely many errors. And I happen to observe only one. Okay, so in your problems, oftentimes you just observe a single realization of y. And you compute a single realization of beta hat. And you get a single realization of E. But once we elevate to this probabilistic framework, beta hat is an ensemble of values. E is an ensemble of values. Y is an ensemble of values. And so we don't care about like a single one. We care about like a distribution of y, for example. What the variance of y. We care about like probability of y or beta hat living in a certain space or like subspace. So these are all happen in this abstract space. Okay. So if you understand this, you're not going to get confused by you go to R, you compute beta hat, you see a vector of numbers, and you're asked, what is the variance of this? You're looking at it, so this is just a vector of numbers. What does it mean for it to have a variance? That particular vector doesn't have a variance. This random beta hat in your mind has a variance, okay? You happen to observe a realization of it. Okay, so this beta hat that from now on we look at, it's not a single it's not a single vector. It's a random quantity. It's like an infinitely many values. Does that make sense, people? I hope this makes sense. But if this distinction is confused, you're gonna get very confused at some point. You're looking at things that are like numeric, but you're talking about variances. You're not going to see the variance in action unless you repeat the experiment many times. If you just see one example of the data set, you're not going to get it. But if I tell you that the data is like this, you can go in R, like fix a beta, this is going to be fixed for us, and fix X, and generate multiple like instances. Randomly sample epsilon, create Y, and get beta hat. And other times you create another epsilon, create another Y, create another beta hat. And once you do it repeatedly, then you can see the variance of the covariance of beta hat, like these quantities, okay, on average. Is that clear? So from now on, we're going to work with this random quantities, okay? And then I'm going to talk about, for example, assumptions about this. First, about the expectation. So this is a random vector, that's covariance, and then distribution, and then the same properties for the other quantities. Questions? Okay, so this is a transition point. Hopefully, now this has some like probabilistic meaning, this equation. So in this equation, I'm going to assume that epsilon, which is going to be random, this is going to be the random quantity. This is fixed. So the error, we can call it the error. The expectation is 0 as a random vector, and the covariance is going to be sigma squared in. This is the first assumption I'm going to make. Let's call this E1 because it's about the error, and it's the first assumption I'm going to make. At this point, I'm not going to give you beyond this, so this is the only thing that we're going to assume, and then derive a couple of results. So what does this particular form of covariance mean? What can I say about the coordinates of? Epsilon has a bunch of coordinates. What do we know about the coordinates? Yes.
Each coordinate has the same variance.
Yes, that's one fact. So every coordinate will have the same variance. And the fact that the non-zero elements of the covariance matrix are 0, what does it mean?
Independent.
Okay, good. They're not independent yet. They're uncorrelated. Okay. You just know that they're uncorrelated. I just want to make sure that so you're not talking about the distribution yet. In order to talk about independence, you need to know something about the distribution. At this point, this is only a second order property. We know that they're pairwise uncorrelated. So covariance of epsilon I and epsilon j is 0 if I is not equal to j, which means that they're uncorrelated. Okay, good. And so these properties now tell me something about the vector of y. Y is going to be random, and it will have because part of it is random. So it's going to have an expectation, and I can compute the expectation. So what is the expectation of y? Yes. Yes. It's 0 by assumption. Okay, yes, great. So x beta is fixed. It comes out of the expectation. This is a linearity of expectation application. And then the expectation of epsilon is 0, so you get x beta. Good. That one, okay. Any questions? Linearity of expectation. Okay, we can also do covariance of y. We'll have a covariance matrix. So it's going to be covariance of x beta. Let's see who's brave enough to answer this one. X beta plus epsilon. Yes, I know you're brave, but go ahead. It could be a
First, I just use the definition of variance with the expected value.
yes, we can do that, but I want to avoid doing that. There's a simple way of doing it, yes.
Suppose epsilon. Yes, for x beta is mistakes. So
Yes. It's going to be just the covariance of epsilon. Why? It's constant. It's like a vector, like there's some b. Actually, it's mu. Let's call this mu because we'll kind of call it mu. Mu is fixed and it's a constant shift. And shifts don't change the covariance. Because if you remember, it's defined based on the centering. So once you center the variable, like the vector, the constant shift would go away. So it's insensitive to the constant shifting. So it's going to be covariance sigma squared, sorry, covariance of epsilon is going to be sigma squared I. So it has the same covariance structure, which means that there is no correlation between the observations. This is a statement about y, so the coordinates of your observations are not correlated. It's inherited from the assumption about the noise, and also the variances of them are the same. Equal variance, no correlation. This follows from the assumption. Okay? If you want, you can go write down the definition and you should get the same thing. Okay? That's gonna be always a good idea if you don't remember properties. Just want you to remember these basic properties. Okay, we'll add a stronger assumption later about the normality of epsilon, but for now, this E1 is going to be enough. So we're going to do the two next results based on this simple assumption about the expectation, the covariance of the noise. So first, beta hat is a linear function of y. I've written it here, and then we call that matrix A, as we have done multiple times before. So beta hat is AY. Now I can ask what is the expectation of beta hat, which is the expectation of AY. What would this be? Yeah. BA, or can you say that again?
I mean, so after you take the expectation of beta hat, it turns into expectation of AY. A is just the constant in this case, so then it'd be A expectation Y.
Okay, yes, good. A times the expectation of Y. And this is by linearity of expectation again. Okay, so A is a linear operator, comes out. And what is the expectation of Y? We just did it. Yes. X beta. I guess I get A x beta. What is A times X? Let's do it here. X transpose X inverse X transpose times X. Does it simplify? Sorry? I, yeah, so this matrix is the same as the one that appears there. So it's just a matrix times its inverse, or the inverse of the matrix times itself. It's going to be I. And it's going to be IP plus 1. So this is going to be I. And so this gives me beta. So the expectation of beta hat is beta. Is this good or bad? Good. What is it called statistically? Yes, so beta hat is an unbiased estimator of beta. So we wanted to estimate beta, and we have an estimator whose expectation is beta, which is what statisticians call unbiased, an unbiased estimator. Okay. And again, this ensemble view is clear here because you wouldn't be able to see the expectation of beta hat in practice on a single run, because otherwise you would have the exact beta. You have to run it many, many, many times and then take the average of all of them. Empirically, it would be close to beta hat. So it would be close to beta. But in a single run, beta hat is just going to be a particular vector. Okay, so this happens in our mind at the level of probability, or the abstraction that probability gives. Okay. I hope this is clear. So the covariance of beta hat is going to be more interesting. So let's do cov AY. So what is this one? Maybe someone who hasn't answered today. You did, maybe, okay, back there.
It'd be A that codenames Y A transpose.
Yes, okay, great. This is the formula that we had for the covariance of linear transformation. What is the covariance of Y? I hope you remember the sigma squared I, we just did it. So now what is the next step? Maybe pull the sigma squared out. You get A transpose. I can drop the I as well, so I get sigma squared A transpose. And I'm going to write it like this. So X transpose X inverse X transpose. And then how do I transpose A? Anyone can tell me the rest of the expression?
First one would be X,
X.
but I'm not sure of the transpose.
The other one is symmetric, so it's going to be its own transpose. Okay. There's the product of two matrices. Right, let's say this and this one. So we're gonna transpose the first, the second would be the, and this is, let's say C, and then this is D. This would be C transpose, D transpose. But D transpose is going to be the same as D because it's a symmetric matrix. Because X transpose X is symmetric and the inverse would be symmetric. So that's what you get. This is, sorry, I made a mistake, right? This should be the other way around. The expression is correct, but the naming, this would be D in transpose. Let's not call it, yeah, let's call it D transpose. This would be C transpose, which happens to be equal to C. Okay. The transpose of CD would be D transpose C transpose. And this happens to be also C inverse. You look at it, if that first term is C, then the middle guy is C inverse. So what I get is C squared C inverse C, which is equal to sigma squared C. And it's just sigma squared times X transpose X inverse because that was C. Okay, so once the dust settle, you get like, settles, you get sigma squared X transpose X inverse. So that's the covariance of beta hat, which is just a consequence of the fact that we computed covariance of a linear transformation. That's the first formula. You plug in what the covariance of Y was, which we did the slide before, and then the rest is like matrix multiplication. So this is not a trivial covariance. You can see it's not identity anymore. And so the coordinates of beta hat will be correlated. And this matrix in between is sort of the so-called Gram matrix appears there, which has interesting properties. In particular, for example, this is another manifestation of the fact that X transpose X is a positive semi-definite matrix because the covariance matrix is positive semi-definite. And this whole thing is positive semi-definite. The inverse will be positive semi-definite as well. So another proof that X transpose X is positive semi-definite. But you can prove it easier. There are easier ways of proving. Any question about this calculation? I mean, I encourage you to go through it yourself if you had trouble following it. Just yes.
That's the first part of the covariance, the A transpose is the same as the norm, but is it with
The norm, this is not the norm. You mean A transpose?
times A?
So A is a matrix.
Yeah.
A times A transpose is another matrix. So what you have in mind probably, if you have a vector, let's say beta transpose beta would be the norm of beta.
Yeah.
Let's do it with E because we're going to use it for E. So E is a vector, E transpose E would be norm of E squared.
But A is a matrix.
A is a matrix, yes. Yes.
So
So A transpose is another matrix. A is P plus 1 by N. Y is N by 1. This is P plus 1 by 1. Any other question? Okay, so see what we have here. So the first is we prove that beta hat is an unbiased estimator of beta. On average, it equals true parameter. And then we have the covariance matrix here. And then from this, you can also read the information about the variances and the covariances of coordinates. So variance of beta hat would be the diagonal element of this. And then the pairwise covariances would be off diagonal elements. So variance of beta hat J would be sigma squared, like the J coordinate of X transpose X inverse. And then this is the same. So hopefully these are clear, we're going to use these, but the covariance matrix has a lot more information. Have more information than just these as we'll see. The only problem I have here is this sigma squared is also a parameter which is unknown. So if you go back to the model, really, once we introduce this assumption, we introduce another extra unknown parameter sigma squared there. So both beta and sigma squared are unknown. So as a statistician, I would like to also estimate this parameter. Okay, so this is all good and nice, except that I can't compute it because I don't know sigma squared. How do we estimate sigma squared, anyone? Sigma squared is really, you can think of it as a variance of epsilon I, single epsilon I. Its variance with the sigma squared. How do you estimate it?
Sample variance.
Sample variance, okay. So if I have the epsilon i's, first we note that it's going to be a little bit easier because the mean is 0, so I don't have to subtract the mean. And let me remind you that, for example, if the variance, we write it, it would be expectation of epsilon I squared, because the mean is 0, so it's equal to the second moment. And because they all have the same, so this is for all I, if I happen to know that epsilon i's are also independent, which at this point I don't know, but let's say later we will assume this, a very good estimator would be to replace this expectation with an average, which is like epsilon I squared, which looks like a sample variance. Modulo usually you divide by n minus 1, but here we're not subtracting the mean, so I'm going to divide by 1 over n. So this is going to, under the IID assumption, like if these were independent and have the same distribution, by the law of large numbers, this would converge to the expectation of a single one, assuming IID. The expectation of a single, like the average of a sum of IID entries would converge to the expectation. And so this would give me the sigma squared, which is what I want. There are multiple issues here beyond the IID assumption, which I'm willing to do maybe later. The main thing is that I don't know epsilon i's. Okay, I have no idea what epsilon i's are. However, I have a surrogate for epsilon i's. What do we have in place of epsilon i's? We have the residuals. Okay, I have the vector of E, which is kind of y minus x beta hat. So the epsilon is y minus x beta, the true beta, which I don't know. When I estimated with beta hat, replace it, like plug it into that formula, I get E. So E is the residual, which is the surrogate for my epsilon. So I'm going to potentially be able to estimate if I just replace it like this. So I'm going to just look at the empirical average of these, or if you want, like sample variance based on the residual, okay? Does this kind of make sense? It is an okay estimator, but it's not perfect. And the reason is that you can easily argue that epsilon are like EIs are correlated. They can't be independent. And so I don't have really n independent samples. In fact, if you do, you know that I is I minus h times y, E is I minus h times y. I can actually calculate the covariance of E. Let's do it very quickly. What will be the covariance of E? Will be covariance of I minus hy. Same idea. I get I minus h times covariance of y times I minus h transpose. How do I simplify this? This is the property that I minus h's are A here. Okay, A covariance of AY is A covariance of Y transpose. This is a linear transformation. Same story. So sigma squared I is like the covariance of Y. You get I minus h on this side, I minus h transpose on the other side, but I minus h is an idempotent, like a symmetric matrix. What happens here is a projection matrix.
You just get code y.
Now, com y is like sigma squared I get sigma squared I minus h times I minus h transpose, but I minus h transpose is the same as I minus h. So I can drop that transpose here. And I get I minus h squared, which happens to be equal to I minus h. So the next step is just, this is going to be sigma squared I minus h. Okay, so the covariance of the residual will be sigma squared I minus h. It's not going to be identity. Okay, I minus h is not a general identity. Do it as an exercise for yourself, use the properties of the I minus h. I just want to show that it's the coordinates are correlated. And another way of seeing it is that they live in the image of X curve. So they have to satisfy certain relations. They're not free to be anywhere in Rn. So it turns out that I need to divide, if I want to get an unbiased estimator, this is not going to be an unbiased estimator sigma squared. I need to divide by the dimension of the subspace in which the E lives, which happens to be n minus p plus 1. That's the dimension of the image of X perp. So this is the correction that we need to make, and it will become very clear later on. So this is going to be our estimate. So norm of E squared divided by n minus p plus 1. This estimator is called S squared, and we'll see that this one is going to be the actual unbiased estimator. At this point, it might not be clear, but there are many ways that we're going to work with this, and it becomes very clear for you, hopefully, that this is using the properties of projection operators. I just want to point out that looking at the covariance gives you a hint. The sigma squared I minus h tells you that the coordinates are not uncorrelated, so they can't be independent. So we're not really like taking the average of n independent things. And the actual number of independent coordinates is the dimension of the space on which they live. This is kind of sometimes called the degree of freedom here. And so we have to divide by that. And we'll see that more precisely later, okay? So we have an estimate of sigma squared. Now I get so if I look at the covariance of beta hat, which is sigma squared X transpose X inverse, I get an estimate of this covariance, which is going to put a hat on top of the whole thing. So I get an estimate of the covariance, which is going to be S squared. This is a plug-in estimator. Okay, so I can get a plug-in estimator of the covariance matrix by replacing sigma squared with S squared, and this now I can calculate everything I know. So S squared is defined in terms of the residual sum of squares, or the norm of the vector E squared divided by this quantity. And so I have a good estimator of the covariance. This allows me to do the confidence intervals, hypothesis testing, and stuff like that. So far, so good. This is a little bit tricky. We haven't done like the full justification yet. Just wanted to argue that this is a good estimator if you had it. And then this suggests that we can replace the error, the actual error, with the residuals, but the residuals are kind of correlated. So instead of dividing by 1 over n, we divide by something which is a little bit smaller, right? Okay, so this is like slide is saying it. So now you understand is norm of E divided by n. This will be too small because again, it's going to be biased downward. So E is like this, lives in the image of X perp. And dimension of that space, you can calculate dimension of the space is n minus the dimension of the image of X, which is p plus 1, so you get n minus p plus 1. So really has entries, but degrees of freedom is basically n minus p plus 1. You kind of used p plus 1 degrees to estimate beta. This is the remaining degrees of freedom. Again, these become very clear later on. Okay, so that's the correct estimator or the unbiased estimator. It's very similar to the sample variance, if you remember if you have a sample variance, when you compute it, you usually divide by 1 over n minus 1 because you're subtracting x bar. So you lose 1 degrees of freedom because you estimate the mean. It's the same idea of projection. You're projecting onto the direction of all ones. And you look at the residual, which is xi minus x bar. That's kind of the residual. And so because that space is one-dimensional, the residual will be n minus one-dimensional. So you usually divide by n minus 1. Again, this becomes more clear once we talk about the quadratic forms and their distributions. Here's the same thing, but we're just projecting onto a bigger subspace. We have t plus 1 variables. That particular one is from the intercept. It was just that. If there was no covariate, you just get the sample kind of variance idea. But we get t plus 1 and you get n minus t plus 1. Anyway, so very fast, but in the interest of time, that's all I'm going to talk about for this right now, but we're going to revisit this many times. Okay, so we have an estimate of sigma squared. Any questions? Is it roughly clear? Okay, so let's do E2. So this is enough. This was enough to get the covariance and the expectation of, let's say, beta hat, which is of interest to us, but it's not enough to get the full distribution. Okay, to get the full distribution, I need to assume something about the distribution of epsilon, which we're going to need for confidence intervals and hypothesis. I need the full distribution. So I'm going to assume that the noise vector is multivariate or distributed like a multivariate normal random vector. With the same mean and the covariance matrix that we had before. Okay, so the only thing that I'm going to assume here extra is this normality. Okay, the mean is the same, covariance is the same as E1, so it kind of is a stronger assumption. It includes E1, but more. So it just tells you that epsilon is multivariate normal. And so in particular, what it says is the coordinates are, so if we look at the coordinates, each coordinate is going to be normal, okay? Because the marginals of a multivariate normal distribution are normal. So each coordinate will be normal, and it's not hard to see that there's zero mean and the variance is sigma squared. Each coordinate will have this distribution, but a little bit more. So we know something about the relation of the coordinates as well. So what do I know about the relation of the coordinates? Uncorrelated, but now they're also independent. Okay, so now it's safe to say independent. Now I give you the pass to say they're independent. So epsilon I, epsilon j are uncorrelated, hence independent by normality, okay, joint normality. So the coordinates are independent if they're different, and they have the same distribution, so they're IID. So I can say epsilon i's are really IID, which means independent, identically distributed. Okay, they're independent, identically distributed as normal 0 sigma squared. That's equivalent to, this statement is equivalent to saying that jointly as a vector, they have the multivariate normal distribution between 0 and covariance sigma squared IM. Okay, so that's our assumption about the noise. Independent, identically distributed, normal, random variance median 0, and variance sigma squared. Once I have this, I can now tell you something about y. What do we know about the distribution of y? Remember, y is x beta plus epsilon. What can I say about the distribution of y? What is this, like, as a transformation of epsilon? What kind of transformation is this? Linear?
Yeah.
It's almost linear. It's like affine. Because this is a constant. If you want to be precise, mathematically, you would say affine. Linear is fine with me, but let's be precise. So it's an affine transformation of epsilon, so it's going to be normal. Because affine transformations of multivariate normal random vectors are, again, multivariate normal, or have multivariate normal distribution. So it's going to be normal. All you have to specify is the mean and the covariance, but we know the mean and the covariance. We've calculated this before. They're the same as what we did before because we're assuming the same mean and the covariance matrix for epsilon. So I get y is normal between x beta and variance. Or covariance sigma squared that. So again, the only new thing here is normality, and it follows from the property that affine transformations are again normal. So about beta hat, which happens to be AY. Remember the A is X transpose X inverse X transpose Y. What can I say about the distribution of beta hat now?
Is it also affine?
It's affine, actually in this case it's linear, which is also affine. Affine is more general. There's no constant shift, it's just the matrix times Y, so it's a linear transformation. So this is going to be normal as well by the affine transformation property. And I know the mean and the covariance. So what's the mean? You calculated the mean. Beta and the covariance. X transpose X inverse. Okay, so you have the full distribution of beta hat now. Again, the only thing that we added here is normality, which just passes through to beta hat to Y. The same goes for mu hat, which is hy. This is another linear transformation. E is also I minus h times y. This is also going to be normal. And I'm going to let you figure out. These, the only thing that we have seen, which is not going to be normal, is which quantity? This guy. So this is not a linear or affine transformation. It's a nonlinear transformation. So the distribution of this guy is not going to be normal. But we can figure that out as well. It's a transformation of normal anyway. But almost all the other quantities that we have seen are going to be normally distributed because they're affine transformations of the observation vector, which tends to also be normal. Hidden values, any linear combination of the elements of beta hat is going to be, like if I look at beta hat 1 minus beta hat 2, that's a linear transformation of beta hats. So that would also be normal. The joint distribution of beta hat and E, as we'll see next time, like if you stack beta hat and E on top of each other, this whole thing is going to be a linear function of Y. And so it's going to be, again, multivariate normal. Okay, so you do like stack things on top of each other that they're going to be jointly normal. So they're going to be a cross covariance, which is of interest to us. And it happens to be 0. So beta hat and E will have 0 cross covariance, which means they're independent. It's like an interesting fact. So this will be normal as well. Oh, I mean, we'll figure this out later. Next one. But as an exercise, try to show this normal as well. Just want to argue that this can be written as a linear transformation of something that you know, which is normal. And it's going to be normal. Questions? I'm going to leave fast because I have a little more slides to go through, but I think this is, yeah, okay. So another sequence, for example, because beta hat is normal, multivariate normal. The coordinates are marginal, so those are going to be also normal. So beta hat J would be now a scalar, so it's going to be a usual normal random variable between beta J, the true beta J, and the variance, which is going to be the J coordinate of the covariance matrix. Again, this is kind of obvious from the properties of these. Beta hat, so this is going to be something that we use after the midterm to do inference. Is this clear? So these slides are just like going over all the after E2, you just go through all these quantities that we saw and you just argue that they're normal because they're linear or affine transformations of Y. Okay. Just convince yourself that, and then the covariance and expectation you can compute by the properties, linearity, and the linear kind of assumption about, or like the lemma that we have about the covariance of AY. Okay, one last thing is this remark. So under E2, we know that the Y has this particular form. or distribution, the normal distribution. So as a statistician, once you have the distribution, oftentimes there is a very general approach to do estimation. So you can compute what's called the maximum likelihood estimator of your parameters. Have people seen maximum likelihood? So just bear with me, maybe like 2 minutes. So the likelihood, I would spend like a half an hour talking about likelihood, other like in a different course. But likelihood is something that statisticians like very much. And it's really, in our case, would be you write down the density. If you view it as a function of y, it would be the density. The integrates to 1 and it has the meaning of probability. If you fix y as your observation and look at it as a function of the parameters, okay, so the parameters here would be beta and sigma squared. It's a function of beta and sigma squared, and that function is called the likelihood, okay? So you try to maximize this likelihood, you try to maximize this function of beta and sigma squared, given the particular observation. And the rationale is that this would be the set of parameters under which your observed y has the most likely, or like has the most probability. Like the probability is the highest, or most probable under that model among all the models in this family. So when I try to maximize this, because there's this negative sign here, because the exponential is monotone, maximizing over beta is equivalent to minimizing this quadratic form here, which gives me just the least square solution. So it gives me exactly the beta hat that we had before via the geometric approach. So MLE of beta under this normality assumption is the same as the least squares estimate. Okay, this is a consequence of just the particular form of the normal distribution. The interesting thing is that I can also maximize over sigma squared. Once I have the beta hat, I plug in the beta hat here. Now I maximize over sigma squared. Once I plug in the beta hat, this would be norm e squared. And then it's just a function of sigma squared, univariate function. You can take the derivatives that are equal to 0, argue via the second derivative test that that's a maximum. And that will give you this estimate. So this estimate that you look at the norm of e squared divided by n turns out to be the maximum likelihood estimator. It's going to be a biased estimator, as we kind of roughly argued, not completely, but it's the MLE. And as n grows, asymptotically it has the same properties as squared. So if p is fixed and grows, this is a good estimator asymptotically. It will be asymptotically consistent. You convert this to sigma squared, but for a small n, the other one that I mentioned, the unbiased one is big. Okay, so the least squares make sense without normality, but normality gives this MLE interpretation, which is maybe interesting. And later on, if you change the distribution, let's say if you assume a t distribution, for example, maybe you get a different estimator. Maybe the least squares might not be the best option. If you change the assumption on the error, basically, you get a different distribution for the observations. There's going to be maybe the MLE would be a better estimator there, maybe. Anyways, under normality, they coincide. So the only thing that we changed is this n here. Okay, for good reasons. Otherwise, you could have argued from the MLE principle. Okay, that's it. And then I think this is just the summary. Next time we can come back and do a bit more relations. Thank you.